Okay, we're moving into 3.4. So students, we're just working on this warm-up. I'm going to go over it quick. Summarizing basically what we did in 3.3. Determine the intervals where the graph is increasing, decreasing, and then has the relative extrema. Okay, so the derivative. Oh, I was so nice to give you a polynomial. 4x cubed minus 12x squared. So you should have gotten 2 critical points when the derivative is 0, the horizontal tangents at 0 and 3. And then there's no points where my derivative is undefined because it's a nice polynomial. Okay. In your sign chart, this was the results I got after testing in the derivatives. I did -1 and I got that it was negative. And then I did +1. I got that was negative as well. Then I tested 4 and I got that one was positive. Ooh, interesting. Ooh, finally, something different, right? Okay, so increasing is anytime your sign chart is positive. So 3 to infinity. I'm just going to justify why, because it's nice to have this in your notes because the derivative is positive. That'd be your justification. All right, now decreasing. Hopefully you didn't group this interval all together because technically it's not decreasing at 0. Technically it's constant at 0. So you would have to separate those into 2 separate intervals. So you'd say on -infinity to 0 and then 0 to 3. You can't group those together because the derivative is negative. Okay, do I have any relative max? No. Minimum, decreasing. I have a minimum here when it changes from negative to positive. It does not ever change from positive to negative. No relative max. Derivative never changes from positive to negative. No relative max. And then we do have one relative min right here at 3. Because the derivative changes from negative to positive. Okay. How do we do? Got it? Should we quick look at the graph so you can see what's going on here? Yeah, that sounds fun. Let's do it. 4 x to the... Oh, sorry. No, I was about to type in the derivative. X to the 4th minus 4x cubed. All right, well...
I did -30 as my y max.
Okay, and that fit pretty well.
And then my y max, x max, 5.
Did you go 0 to 5?
No, I went -3 to 5.
Okay, then keep mine. Oh, beautiful. Love it. So my critical point's at 0 and 3. So you can see how I do have a horizontal tangent here. But it's not a min or a max, and it doesn't change, from increasing to decreasing or decreasing to increasing. It's decreasing, constant, decreasing until you hit this relative. And it looks like it's also the absolute min. And then that horizontal tangent, and then okay. So I like this example too because it kind of leads into 3.4 because there's something else interesting that happens at this point that that the first derivative doesn't really allow us to find. We have to use the second derivative. So we'll just kind of quick talk about something called concavity. So it's basically like another characteristics of our graph. I don't think you've probably heard of concavity before. Usually that's kind of new in calculus, but we use like the second derivative to help us with concavity. So let's just try to like understand what concavity is today, and then we'll see if we get into any practice problems. So concavity basically like refers to kind of like the shape of your graph and like how it bends and turns. So there's two types of concavity we can have. And you kind of do this with parabolas where you say it's like, oh, it's U up or it's U down. Technically, the true vocab word for this is concave up or concave down. So this occurs a lot in like our polynomial functions where we have these like little like changes in like the shape where it switches from like concave up to concave down, vice versa. So when it's concave up, I kind of think like concave up like a cup, concave down like a frown is how I kind of remember it. So here we talked about how like our first derivative helps us locate how our function is increasing or decreasing. So now basically we're going to look at how the slopes are increasing or decreasing. Okay, so we're kind of looking at like the derivative of the derivative, if you will. I found this one chart that I really like. But basically another way to think of concave up here is like that the graph always lies above the tangent lines, like all the points of tangency, the tangent lines would be below the graph. And if it's concave down, all the tangent lines would lie like above the graph. So I have this visual that I found on Desmos this morning, right here. Oh, yes. Okay. Now this black curve is my original function. So if I'm looking at a cubic, this slider here, this is giving you all the slopes at the tangent line. And then the red graph is a graph of the derivative. So like here, for example, when the slope is negative 2.08, my derivative has an output, my slope equation of negative 2.8. Okay, we talked obviously a lot about like connecting the horizontal tangents. I can't get that exact, but that's pretty close to 0. When I have a horizontal tangent of 0, then my derivative is 0, right? Okay, so what we're doing with concavity is we're looking at how the slope is changing. We're looking at the rate of change of like the slopes. So if I go from about way down here, so as I'm moving this point up, this is like concave down, right? Of my curve, I have concave down until like around here, and then it's like now it's switching to concave up, like a cup. So watch what's happening to my slope. So here I have a really, really big positive slope, a steep 10. All right, so are my slopes getting bigger or smaller? Smaller, right? So my slopes are decreasing until I get to 0, but they're still decreasing, right? Now they're getting more and more negative until I get to about here. And that looks like it's about the steepest slope of my curve right here at -4, and that's like the lowest point on my derivative, right? It makes sense. That's like the most negative our slopes get, is that point right there. Okay, so that piece, or to highlight this in green, this piece we would call concave down because the slopes are decreasing. And you'll see how this now links to like where our first derivative is decreasing, where our slopes are decreasing. I think I just moved it. Yep, I did. All right, now if I look at, let me get a different color here. How about orange or something? Now if I look at this piece, where now I'm like, okay, now it looks like concave up, like a cup. Let's see what our slopes are doing. So right now it's the most negative it can get, -4. And now, I'm trying to go slow, but it's hard. Now it's at -2, -1, 0, and now they're becoming positive. So my slope's getting bigger or smaller?
Bigger.
Bigger, right? My slopes are increasing. And since this is showing you the graph of the derivative, you can see right here that my function changes to increasing. Okay, so that's what concavity like tells us about our graph. So what else do I want? That's what this part is basically saying. When your derivative is increasing. When your slopes are increasing, we have concave up. When your slopes are decreasing, getting smaller, really, really, really negative, it's concave down. Okay, I like this visual too. So the way that it makes the most sense in my head is like concavity tells us how a function like bends or turns. So if I were to look at just like my basic polynomial cubic function, we can see from here to here would be concave down, like a frown. Now we have something interesting going on here where all of a sudden it switches. Orange again. And now it's concave up. So we know it's concave up if our slopes are increasing. So if the first derivative is increasing, think of this as slopes. Let me do that one in orange to match my color coordination here, because concave up I had an orange. So concave up if our slopes are increasing. Similarly, concave down if our slopes are decreasing. Okay. Now let's quickly look at our graph of the derivative. So kind of ignore the actual function for a second and look at this parabola. What do we notice about our derivative graph from here to here when we're concave down? All the slopes are what? Negative. So if I were to take the derivative of this, those would all be negative, right? If I were to take the derivative of this, these would all be positive. So basically, the derivative of the first derivative, what we call the second derivative, anytime it's positive slopes, we can conclude it's going to be concave up. Anytime our second derivative is negative, it's going to be concave down because it's referring to the derivative of the derivative. So it's kind of like taking the first derivatives test of the derivative function. So we can locate like where our first derivative is increasing and decreasing, and then link that back to concavity of the original function. Okay, sorry, I didn't mean to go over time, but if you didn't write this down, no worries. We can pick it up on Monday, and me, I'll probably be explaining anyways. Like I like to do.